And this is why we have the workshop today, because we want to show you, okay, how can you actually start the development of a ROS2 manipulation cell to really start developing these kind of adaptive and scalable robot applications. The setup today is basically using Solidworks in the beginning, and we have a small plugin there that has been contributed by the ROS community. We have done a few changes there to make it a little bit more usable with ROS2. It's not yet in the main line, but it hopefully will get there. And then we have the ROS2 setup, which is basically, well, a humble version that we're using there, plus the UR robot driver in specific versions. And what are we going to show here? So first, we're going to show, okay, how do you actually export from the CAD program to URDF, specifically your cell, so you have the digital twin of your cell for your application available. Then we're going to show you how you basically combine component description packages, so how you combine the cell with the robot and the gripper. And finally, we're going to get into how you actually create from that model that you created then your Moveit configuration package, including the planners and the hardware interface to the robot, basically the integration of the driver. So in total, what we're going to create there is basically a few packages. So we have the static cell description, which we are going to export from the CAD program. Then we have the robot cell description, which is basically the composed model consisting of the robot cell, the robot itself, and the gripper. And finally, we have the robot cell Moveit config, which is basically the motion controller configuration. And that's what we're going to show. And with that, I want to give over to my colleague, Ragesh, who's going to do the presentation here.
Yeah, I'll take over. Thanks. Is this, am I audible? Yeah. Perfect. So I'll briefly walk you through the process that our team undergone during this process when we started from a CAD model all the way to the system integration. The first step being the CAD to URDF model, CAD to URDF process. So our system setup consists of three main components, which are a robot, which is Universal Robots UR5E, and then we have a custom-made robot cell, and then we have a gripper from Schunk, which is Schunk EGP50. And so this is what we had in our hand, and what we need to do was to compose everything into a URDF and then have Moveit integrated into it, and then integrate the entire package into the computer, into the robot's computer. So that was our problem statement. So the first step being conversion from 3D CAD model to Zacro or URDF. That was our first step in the process. And for this process, we had this URDF exporter plugin, which came in handy. So this is, yeah, as my colleague Christoph mentioned, it's still not in the pipeline, but it's the pull request is there yet. So using the URDF exporter plugin in SolidWorks, I will show you how this CAD export is being done. So to just give a brief brief overview of what URDF is. URDF is just Unified Robot Description Format. It's an XML specification where we can define robot manipulators and mobile robots, anything with links and joins. And the specification covers the kinematic and dynamic description of the robot. It can also do the visual representation and the collision model of the robot. And as I said, I have mentioned a word called Zacro. Zacro is nothing but an XML. Zacro is an XML macro language. We actually use Zacro to clean up the URDF in a sense that we use parameters and macros, which is not available in normal URDF. And so let me play this video. Yeah. So this is the SolidWorks tool that we use. And in the SolidWorks, if you go to tools, we can see the export URDF plugin because we already installed it. We can see that in the tools. And the first step we do is to import the CAD model, or we develop the CAD model inside SolidWorks. And then the next process is to choose the base link or define the links of the model. So here in this case, we don't have much joins or links, so it's just a base link which we already added. And the next step is to preview. So now we are trying to preview the model and see on the bottom we see origin or the base link. Um, yeah, somewhere over there. Yes, that's the origin. But we see that this is not according to the ROS convention because the z-axis is pointing to somewhere and the y-axis is pointing downwards. So according to ROS convention, we need to have the z-axis pointing upwards, and yeah, so we need to change that. So it's possible to do that. So we can click on that and then we can change it using the tool. So we select which direction the x-axis and the z-axis should point. And once we are done with that, once the origin is or once the base links axis is perfect, the next step we can do is to export it. And here, in order to export, we need to export the meshes and the URDF because we wanted to visualize that later in RVs and Gazebo. So having STL files is super important for us. So this is the last step where the STL files or mesh is being exported. Yeah. So the link is correct. We just click on the link and then export URDF and meshes. Yeah. Yes. So once we have this exported directly from SolidWorks, it's now much easier to use it on a ROS package. And so, yeah, in this step, we have shown that how this SolidWorks export happens and how the exported cell description can be viewed in RVs. So in the coming slides, I'll show deeper on how we compose these existing components into a larger unit. So this in this step, we talk about the composing the kinematic chains of individual components. So here, as the system consists of three different components: UR robot, the Shunk gripper, and the custom cell that we have. The UR robot already have the ROS2 description, so we can directly use it. And then Shunk, we also have that for Shunk. And the one on the robot cell description is the one which we exported in the previous step from SolidWorks. So we combine all the three in this step using Zacro, as I mentioned before. So I'll try to include all these files. So here on the right side, you see that the file has been included, and I just need to connect the links in the right way. And in order to make this task a little more easier, we have a Visual Studio Code extension, which we use for most of our development. And this is really useful because we can see that on real time or how the kinematic chain is being connected. So if there is any issues, we can resolve it right here, and it speeds up the process. Because if we don't have an extension like that, then the only way is to preview it using using RVs, which is not so easy. So we need to roll back and forth in order to get it through. And the next step is to create the robot cell description package, which is basically combining all the three different packages using the Sacro and create one final cell description Sacro. And the result is something that you see on the right side. This is an ROS preview, which consists of all the robots, and the TF tree is being also shown here. And so I just have a heads up here. So the export from SolidWorks have the meshes that is being exported from SolidWorks have very high complexity. And because of that, for this at least for this demonstrator, to keep it simple, we just used primitive geometric shapes, and we built the cell using just boxes, using cuboids and cuboids mostly. And even for the Shung gripper, we created a mock demo using the primitive shapes. Um, so this is one problem that we observed during this process, and in order to simplify that, there is option which is to use FreeCAD or some other software to simplify the meshes and then export it again. Yeah, but for the simplicity, we just went ahead with this. And once we created a final robot description package, we just try to visualize it, and which is using RVIS. Nothing fancy in that. We just use robot state publishers and just launch it. Yes. So this is what the final output looks like once the package has been created. So we can also check to control individual joints using joint state controller. Yeah. So that's basically the output of the first step, which is creating the robot description package. So once we have the robot description package with us, the next step is to create a Moveit configuration. And this is the most important step to get into to integrate with Moveit. So for this, we have this Moveit setup assistant wizard, which helps us ease this process. I would say the first step is to just is to export or to browse for the particular files that we created in the previous step, add that Zacro file in, and just load the files. Once we load the files correctly, or if the files are good enough, then we are able to see the preview on the right side, which is a very small preview. This is also one of the glitch, or I would say it's like one of the bug with the RVIS Moveit setup assistant wizard. It needs to be fixed as well. The next step is to add the collision, self collision checking. And in order to do that, just click on generate collision metrics on the wizard, and it does it for us automatically. And so this is how the generated collision checking would look like. In order to just make it appear better, we can click on the matrix view on the bottom. So it gives us an idea of which and which between which and which links the collision checking happened. We can also modify it from here. And the next step is to define the planning groups, which is to combine the set of joins and links to a particular group. So here we must have two groups, one for the arm and one for the end effector. So for the arm, we define it simply by group name arm, and then we add the kinematic solver, which is the default one is KDL kinematics plugin, and then we use the group default planner, which is RRT Connect, which is also default one. And then we click on add kinematic chain, and then the kinematic chain is added. We can expand it all, and we see the entire set of links. And here, one important step is to create the base link and the tip link. So the base link is the base link, and the tip link is the tool 0. Yeah. If you wanted to add one more robot near to that. So I think in order to do that, you can define it in the URDF itself, that you have two robots. So you define the you are in URDF that you have two robots separated by this distance, and that's the world. So you export it into it, and then you create different planning groups, one for one robot. So say that you have one robot for left part of the doing that. So you say that arm left, and then you have arm right, and that's how you define the planning groups. Yeah. Did I answer you? Yeah. Yeah. So we add the base link and the tip link. So to define the kinematic chain from top to bottom, and save it. And as I said, like we have another group here, just to give an idea about the gripper. So we have gripper, and gripper also has some links and some joins. So we add the group name gripper, and we don't need to add any solver or default planner for the gripper. And we click on add kinematic chain. The same thing happens. We can just expand it, And then we add the base link for the grippers planning group and also the tip link for the grippers planning group. And we did that, save it. And the next step, this is not really useful step, but we can actually define a lot of robot poses. This would be useful if you have some pick and place application where you know the predefined poses where the robot is going to be all the time. So you can define point A, point B, and save it. So later in the application development, you can just ask the robot to go to point A, point B. So it would directly go there with the join values. So I just created a home position. I just positioned the robot into a home state, which the robot can stay default. And I added that. So the next step is to define the end effector. So I define the end effector name, and also I define the end effector group, which is the gripper, which we named it before, and the parent link to which the gripper is being attached, which is the tip of the UR5, so which is tool 0. And then the parent group is arm. So that being added to the step. So ROS2 control, we don't need to modify anything over here. We can just jump on to the next ROS2 controllers. Click on auto add robot join trajectory controller. It would add the default controller for us. For Moveit controller, do the same thing. Click on auto add, and it will do it for us. In this demonstrator, we don't have any 3D perception sensors added to the setup. But if you have already one 3D sensor for your application, then you can select on this. You can add a 3D depth camera or a point cloud source from here. Then it shows the set of desired launch files that the Moveit setup wizard would export. And the next step is to add the user, and the final step is to generate the configuration files. So these are the set of files that are being generated by the wizard, and click on generate package. And yeah, if everything goes well, it says that okay, it's been successfully exported, and you can exit the setup assistant wizard. So this is what the exported files, or the files that is being generated by wizard looks like. It consists of a config folder, it consists of a launch folder, and inside config folders you have all the configuration files. And it misses certain files, like the planner plugins are not, or the planner configuration files are not being there. So in the next step, I'll show you how we add that configuration into the config folder. So planner configuration, this is very important for Moveit. So there are few planners that are available, which is Chomp, which is gradient-based trajectory optimizer, and then you have OMPL, which is the default motion planner for Moveit, and then there is from PILS, the trajectory planner for standard motions for like point-to-point and linear and circular motions. So based on the application, we can select which planner we need, and so each Moveit planner requires one or more configuration file. And where do we find these configuration file? So that's the question. So these configuration files are just YAML files, and the location of and the file name matters, because the launch file that was being generated, it looks for the planner files in certain locations, and if it doesn't find it there, it's not going to load those controllers, or sorry, the planners. And it mainly, the planner configuration file, the YAML file has mainly 3 sections, one being the planning plugin, and request adapters, the planner specific configuration section. So there is actually a lot of Moveit, there are a lot of planners available in Moveit resources. It's in the GitHub repo of ROS planning. And so we select the ones from Panda Moveit config, and inside the Panda Moveit config and under config directory, we find a lot of underscore planning suffixed planners. So we select whatever we want for this application. So for this application, we select Chomp, we take in the OMPL YAML, and also we take in the PILS industrial motion planner for this application. So this is what we did. We just copied over the right files to the config folder of the generated file, the Moveit generated file. So this is actually important step. That's why I am stressing it here. So once we have the configuration or the config files ready, the next step is to launch with fake controllers, which is to generally launch the digital twin of the entire setup. So yeah, we'll launch the virtual twin of the cell in RVs. This can be done by launching demo.launch generated by Wizard. And once we launch it, we get to see the digital twin. And on the left hand side on the control panel, we can just plan according to the positions that we give. So here we click on plan and then we can execute it. So the robot just follows that using the planner configuration that we added. So yeah. So once we reach this step, we have one step closer to the hardware implementation. And now comes the most important part where we spend a lot of time to understand how to do that. To create the real hardware launch file. Um, we spend a lot of time here because none of these things are available. In the sense like how to put all of these puzzles together to create this big picture was not clear for us. And so these 5 components are really important for launching the hardware setup. For the robot state, we need the robot state publisher and virtual joins. And for motion planning, we need the move group. For user interface, the one which we saw in the digital twin side, we need the Moveit AVIS. And from UR driver side, we need UR ROS-2 control node, dashboard client, and controller stopper. And from the controllers, we need spawn controllers. And I'll walk you through the launch files. Um, from yeah, so for here, we are adding the virtual joined launch file and the RSP launch, which is the robot state publisher launch files, which is generated actually by the Moveit wizard. And the next step, we add the move group, which is also being generated. Then move it RVs being added to the launch file. And then from the UR driver, we just add those nodes that we need to start, which is basically UR ROS-2 control node, the dashboard client, and finally the controller stopper. And then for spawning controllers, we add that too, which is also being created by our wizard. And finally, yes, now we are ready to launch the real robot in your work cell, in your robot cell. So this is our final result. The one on the bottom is the real robot that you see, and the virtual twin on the big picture. And we can give the input from the um, RVs side, and then create a plan and then execute it on the real robot and also on the virtual twin. Yeah. Yes. So uh, this is something that we learned. So if you know what you do, you can set up a cell in no time. But for us, it took a very long time. And that's why we created this workshop so that we could share this idea with everyone. So we just wanted to share with you some of the issues that we faced and some improvement potentials that we would like to propose. So basically, hardware integration is still difficult task. Yeah, there is a lot of learning that one need to do and have a deeper understanding of all the underlying technologies and concept in order to do the robot integration. And there are some improvement potential that we would like to propose, that especially for Moveit Setup Assistant 2, adding planner configuration file automatically would be a great help for us, because it took us some time to figure out how to find these configuration files and put it manually into the correct locations. But it would be great if it is automatically generated from the setup assistant or Moveit Setup Assistant wizard. And from the driver side, it would be great if they could provide some information on which nodes need to be started and which parameters are required for the nodes. Um, yeah, because we had to do a lot of quite reverse engineering to understand what are the nodes that are required to get it running. And for the launch file, yes, Python is nice, but launch files are a bit complicated, and it would be nice if it would be made much more simpler. And yeah, so now I'll hand over to my colleague, Christoph.